Hello everyone, welcome to our presentation entitled CommonRoad-Reach, a toolbox for reachability analysis of automated vehicles. I'm Edmond Irani Liu from the Cyber Physical Systems Group, Technical University of Munich. This work has been done in collaboration with my colleagues Gerald Wörsching, Moritz Clichat and Matthias Althoff. Compared with human-driven vehicles, highly automated vehicles are expected to offer increased road safety and passenger comfort, reduce emissions and travel time. However, major challenges such as strict safety guarantees in critical situations, decision-making and motion planning in small solution space are yet to be resolved to unfold these benefits fully. Reachability analysis, which determines the set of all reachable states of a system over time, which is also referred to as the reachable set, is a powerful technique to address these challenges. Despite reachability analysis having been well researched over the past decades with continuous improvements, publicly available toolboxes are either not real-time capable for automated vehicle-specific applications or do not take into account time-varying forbidden states originating from traffic participants present in a scenario. In this work, we present CommonRoad-Reach, which is a toolbox for computing the reachable sets of automated vehicles for motion planning applications. In the figure on the right, we show an exemplary reachable set computation result projected onto the position domain, which is called the drivable area. Our toolbox integrates two methods for reachable set computation, namely polytopic set propagation and graph-based propagation. Furthermore, our toolbox integrates the function of extracting collision-free driving corridors from the computed reachable sets. We provide Python and C++ implementations of the algorithms, offering convenient prototyping and real-time computation for the users. We now proceed to the preliminaries. The scenarios in our toolbox are described in the common road format, which consists of a road network and environment elements such as obstacles and traffic signs. We use the most likely trajectory as the prediction of other dynamic obstacles, but our toolbox is also adaptable to other prediction methods, such as set-based or probabilistic-based methods. The toolbox is able to compute the reachable sets in both the global Cartesian and local curvilinear coordinate systems. For the latter, we require a reference path from which the coordinate system should be constructed. We abstract the system of a considered ego vehicle with a point mass model, with two second-order integrators in two orthogonal directions, zeta and eta. Within the Cartesian frame, these corresponds to the x and y directions. Within the curvilinear coordinate system, these corresponds to the longitudinal and lateral directions of the reference path. At a step k, the state of the system consists of positions and velocities in the two directions. Also, the system accepts accelerations in these two directions as the input. The discrete time dynamics of the system is given as shown. In our work, the reachable set is defined as a set of states reachable from the initial set of states, while avoiding the set of forbidden states. Since the exact computation of this reachable set is difficult, we instead over-approximate the reachable sets and represent them with the unions of so-called base sets. In the figure, we show the polytopes constructing the base sets, as well as its projection onto the position domain. Again, this is referred to as the drivable area. To store the spatial-temporal relationships of the base sets, they are stored in a graph structure named reachability graph. In the graph, each node corresponds to one base set, and an edge connecting a parent node to a child node indicates that the child node is reachable from the parent node after one step. As mentioned earlier, a drivable area is the projection of a reachable set onto the position domain. In general, drivable areas may be disconnected due to the presence of obstacles. Thus, the notion of driving corridor can be defined. A driving corridor is a sequence of connected sets over steps 0 to kf, where kf is the final time step of the computation. Here in the figure we show a situation where there is a crossing pedestrian and the ego vehicle detects two driving corridors. The corridor on the top corresponds to a braking maneuver in which the vehicle would stop in front of the dynamic obstacle. The corridor on the bottom corresponds to an evasive maneuver through the narrow gap between the obstacles and the road boundary. The CommonRoad-Reach toolbox offers the computation of reachable sets and extraction of driving corridors. It has the following core modules. The reachable set interface serves as the user interface for setting configurations, computing reachable sets and drivable areas, and extracting driving corridors. The reachable set module is an abstract superclass that instantiates the subclasses for computing reachable sets using the two methods included in the toolbox. For performant computation, the C++ implementation is invoked with the help of the Python 11 library. In polytopic set propagation method, we are able to include time-varying constraints on velocities and accelerations, which is not possible in the graph-based propagation method. In contrast, the second method avoids several geometric operations, rendering faster in most cases than the first method. We refer the readers to our work for more computational details. We now explain the setup of our experiments. The key features of our toolbox are demonstrated by using scenarios from the CommonRoad benchmark suite. It is worth noting that, within the Cartesian coordinate system, the CAM's friction circles is approximated with a box. In contrast, within a curvilinear coordinate system, we assume that the ego vehicle follows the reference path. Thus, we use more conservative parameters for the longitudinal and lateral driving directions. The first scenario illustrates an urban driving situation with a static obstacle in front of the ego vehicle and another vehicle approaching from behind. It can be seen from the animation that the computed drivable areas detect the narrow passage on the left side of the static obstacle. Our second scenario is a four-way intersection with the presence of two other vehicles. This computation is done within a curvilinear coordinate system. We further use this scenario to demonstrate the extraction of driving corridors. At time step 30, we see that the drivable area is disconnected due to the turning vehicle V1 at the intersection. Thus, the drivable area exhibits two connected sets C1 and C2, each belonging to a separate driving corridor. The two driving corridors correspond to two different tactical decisions. With the corridor on the middle, the ego vehicle would brake in the middle of the intersection before vehicle V1. In contrast, the corridor on the right represents a maneuver where the ego vehicle would accelerate and continue turning right through the gap between V1 and the road boundary. For comparison, we also show the computation result in this scenario within the Cartesian coordinate system. Our last scenario depicts a highway scenario that is obtained from the ngsim dataset. We carry out a computation in a curvilinear coordinate system using a planned route as the reference path. The results show that our toolbox robustly handles the computation of the reachable sets of the ego vehicle in scenarios with multiple dynamic obstacles and can detect narrow gaps between vehicles. To evaluate the performance of our toolbox, we have benchmarked it against 100 randomly chosen scenarios from the CommonRoad benchmark suite. For both propagation methods, computations within the curvilinear coordinate system are faster than within the Cartesian coordinate system. This is because in curvilinear coordinate systems, we used more conservative parameters in both the longitudinal and lateral directions. As expected, the average computation times of the graph-based propagation method are shorter than those of the polytopic set propagation method, due to the reasons described earlier. The computations took a fraction of the planning horizon and rendered the toolbox suitable for real-time applications. To conclude, in this study we present CommonRoad-Reach, which is an open-source toolbox for computing reachable sets and extracting driving corridors for automated vehicles. It integrates two methods from our previous works for reachable set computation. By providing Python and C++ implementations of the algorithms, Our toolbox offers both prototyping and real-time capabilities to users. And we demonstrated the performance of our toolbox through benchmarking against Honda scenarios from the CommonRoad benchmark suite. The toolbox is available at commonroad.in.tum.de. If you are interested in the toolbox, you can visit our website to access the source code. Thank you very much for listening.